to welcome everyone to our Munich AI lecture series, which I think is the first talk this year. It's my pleasure to introduce our invited speaker of today, which is Peter Flach. So welcome, Peter, and thanks for having accepted our invitation. So actually, I guess Peter doesn't need a big introduction for an audience with a machine learning background. And I'm pretty sure most of you already know him, at least by name, perhaps from his research work, or perhaps from his great machine learning textbook, Machine Learning, the Art and Science of Algorithms That Make Sense of Data, which published about 10 years ago, has become a key reference in the field and has even been translated already to many other languages, even such languages such as Mandarin and Japanese. So a few words about Peter. Peter graduated in electrical engineering at Twente University in the Netherlands in 1987. And he did his PhD in computer science at Tilburg University, also in the Netherlands, in 1995. In 2000, he went to Bristol in the UK, first as a reader at the university, and meanwhile, he holds a position as a professor of AI there in Bristol. So Peter is widely known as an internationally leading machine learning scholar. He was editor-in-chief of the Machine Learning Journal for about 10 years. He served as a program co-chair of several major international conferences in the field. He is a past president and current vice president of the European Association for Data Science, a fellow of the European Association for AI, and also of the Alan Turing Institute for Data Science and AI. So Peter made important contributions to various branches of machine learning, more classical approaches linked to logic and symbolic representations, but also, for example, on kernel methods for structured data, on probability estimation and classifier calibration, more recently also on human-centered AI. He is generally quite interested in foundational questions in data science and machine learning, connections between logic and probability, links to philosophy. And I think this also fits very well with his specific interest in performance evaluation. He has worked a lot, for example, on ROC analysis, extended ROC curves in various ways, and proposed other measures, and all kinds of related curves, such as Breyer curves, precision recall gain curves, and so on. So it comes at no surprise that performance evaluation is also the topic of his talk today, which is called The Highs and Lows of Performance Evaluation Towards a Measurement Theory for Machine Learning. And with this, Peter, I hand over to you. So thanks again for being here. And we are all very much looking forward to your presentation. Just one final remark for those people who participate by Zoom. You can ask questions either in the chat, and I will read them later after Peter's presentation, or you can ask him directly. Those people following on YouTube, you can't do that. You can't ask directly. So those people, please put your questions in the chat, and I will read them to Peter after the presentation. But now, Peter, the floor is yours, please.
Thanks, Heike, for this kind introduction, and thanks also to the organizers for the invitation. It's great to have the opportunity to talk to you today. So just before I get started, so this presentation is run in the browser. So actually that URL that you see there at the bottom, flach.github.io/slides/2023_Munich, that actually if you wanted to follow the slides in the browser, then you can do that, and you will see exactly the same as what I'm projecting now. So let's get started. So what do we care about measurements? Well, there are basically at least two reasons why measurements are important in data science, in machine learning, and AI, because actually our data itself are measurements. So we have data about maybe Fisher's iris data set, we have petal length and petal width. So somebody went and measured the petal length and petal width of these flowers and then translated that into data. And already there, you need to think about measurements. So for example, what scale are measurements expressed? What operations can you take? So for example, even if you do an average, a simple arithmetic average, then you're assuming a linear scale, which may or may not be the right thing to do. So, but that's not what I will be talking about today, although I think this is also an undervalued topic in machine learning. And in fact, Eike mentioned my book, and people who look at my book will see that I put a whole chapter on features in the book, because in machine learning, we don't talk enough about features and what we can do with them. But that's not what I will talk about today. Today I'm going at the meta level and talk about performance metrics. So once we have used those features to learn a model from data, we want to measure how well the model performs. And so again, we are measuring things. For example, we form a confusion matrix on a test set. And so counting is measuring. And so we need to think a little bit about what we can do here. What are admissible statistics? What are operations? How do we average? And so on. So there's a link here at the bottom. This is a link to a project that was funded by the Turing Institute to look at foundational issues of measurements. So a lot of what I will talk about today came from that project. So let's do a little bit of a quiz. It's a bit hard in an online setting to do audience participation, but so what's hard about performance measurements? Well, let's say we do something like cross-validation. Let's say we do twofold cross-validation. So we train on one half of the data and test on the other half of the data, and then we swap. So now we have two test sets and two accuracies on those two test sets, two confusion matrices. And so we can ask ourselves, what can we say about the relationship between the accuracy of the classifier on the individual test set and the accuracy of the classifier if I put those two test sets together? So is the accuracy on the entire data set equal to the average? And here I mean the arithmetic mean of the accuracies on the separate parts. And if you think about that for a few seconds, then you would say, yes, as long as those two parts are of equal size. And if they're not of equal size, then I need to take a weighted arithmetic mean. Okay, so this is well behaved. What about things like true positive rate, which is kind of the recall on the positive class, and you can also talk about the true negative rate, which is the recall on the negative class. Something similar happens, but this only holds when the parts have the same class distribution, which is why we often do stratified cross-validation, meaning that we split the data in such a way that in each fold, I have roughly the same class distribution. So there are a couple of conditions, but otherwise everything is well behaved. However, this is not the whole story. So what about precision? So in precision, we are actually looking at columns of the confusion matrix. So we take the true positives divided by the predicted positives. And so you can ask the same question. If I have two test sets, I have two precisions measured on the test set. What can I say about the precision if I merge the two test sets together? And actually, that is not anymore an arithmetic mean. It's not, in fact, a mean of any particular kind. And the reason for that is that you don't know how many positive prediction there is being made on each of the test set. And we can't do the same thing as we did with stratifying, because it's not under our control how many positive predictions the classifier makes. So there is something going on here, and if this is true for precision, then it's also true for F-score, which is the harmonic mean of recall and precision. So recall is well behaved in that sense, but precision is not, and therefore F-score is not. So we looked at this a while ago, and particularly people are in the habit of evaluating F-score using precision recall curves, which were perhaps inspired by ROP curves. So a ROP curve, receiver operating characteristic curve, plots the true positive rate on the y-axis against the false positive rate on the x-axis, and sort of you can calculate the area under the curve, and that is pretty well understood. But precision recall curves are actually behave quite differently. So I call this an earlier result. It was actually published just over 7 years ago, but 7 years seems to be a long time in contemporary machine learning. So, so here we set out to make precision recall curves, which is the little one in the middle, more like ROP curves. And there are all sorts of reasons why precision recall curves are not like ROP curves. For example, you don't see the same linearity in the middle curve that you see on the left curve. And we managed to do that. We managed to kind of linearize precision recall curves, and we call them precision recall gain curves. And let me just spend 1 or 2 slides quickly to tell you what we did, because it kind of underlies this whole research program. So the idea was that we start from precision and recall. So you see the formulas there. Precision is true positives divided by true positive plus false positive. So that's and recall is true positive divided by true positive plus false negatives. So first we take the reciprocals. So we look at 1 over precision and 1 over recall. Now, if precision and recall are in the 0-1 interval, then of course their reciprocal is in the infinity to 1 interval. So the next thing that we do is to basically, we want to map that back to 0-1. And the first thing we do is to actually clip that interval and not quite go to infinity. And there is a justification for that, because very low values of precision and recall can be discarded, because there is a simple way of building a default classifier that always predicts positive, and that will give you a certain minimum precision and recall. Well, always positive gives you a recall of 1, but the precision which is equal to the proportion of positives. So that's justifies why we don't need to go under that value of precision. So we clip this to a finite interval, and then we map it back to the unit interval. And then we get formulas that don't look very intuitive in the first instance, but they have this nice property that you can linearly interpolate between them. And that's why those curves look like this. So on the left, we have a precision recall curve. And so they have these kind of hyperbolic lines are lines of constant F-score. And what we are really doing is pulling the curve upwards to the top right until that hyperbolic line becomes a straight line diagonally, and then everything is linear again. And the nice thing of this curve on the right, this precision recall gain curve, is that we can linearly interpolate, we can calibrate, we can construct the convex hull by visual inspection, which we can't really do on the left. And we can also meaningfully calculate the area under that curve. So that's kind of a little bit of a taster. I appreciate that. I don't expect the audience to have followed the details here. There is a NIPS 2015 paper that explains this more. So this kind of whetted our appetite for looking more at these kind of scale issues and to understand a bit more what's going on here. So this is really what I will talk about today, and this is quite a philosophical talk, because I want to emphasize that actually there are fundamental measurement issues that are not settled. We talk about things like scales and units and types and dimensions as if these are well understood concepts, and I don't think that is actually the case. And so I want to discuss that a little bit and see what the direction of travel in that respect could be. Also, I want to make the point that what we are interested in is often not directly observable. So what we can measure is observable, otherwise we couldn't measure it, but actually the real thing that we're interested in is not directly observable. And of course, we know that in machine learning, we can observe performance on a test set, but we want to know performance on future test data, and that's not observable. And so I started looking at ways of doing this, and we found inspiration in cognitive science, where cognitive psychologists have used methods such as item response theory and factor models to do exactly this, to realize that a student's performance on an exam is only a proxy for their actual knowledge or ability on the subject. And equally, the proportion of students that get the question right is only a proxy for the unobserved difficulty of the question. And so psychologists have developed latent variable models, which of course is something that machine learners understand very well. So we start looking at that. And I will talk a little bit about what we have done in that area, and then I will conclude. Okay, so scales, units, dimensions, and types. So there isn't really, as far as I could find, a definitive framework to link all these things together. So I'll look at it from a couple of perspectives. There is a fairly well-known theory of levels of measurement, which gives us concepts of nominal, ordinal, interval, and ratio scales. And I'll talk a little bit about that, but that kind of stopped at that point, and it's clearly not covering the whole spectrum. Then from physics, we will look at the idea of a dimension. So every physical quantity has an associated dimension. So a unit is different from a dimension. A dimension can be length or temperature or time, and a unit would be feet or meters or Celsius or Fahrenheit. So we look at that, but we also see that there are some issues there. And then finally, we look at what computer science might contribute here. So Stevens' levels of measurements look like this. This was published in Science in 1946, but actually was developed during the Second World War. And this is a table from the paper. And there we have the nominal, ordinal, interval, and ratio scale. So nominal and ordinal are pretty straightforward. And the idea is that if you have a nominal scale, then you can sort of change the labels of the values. You could say, you know, square or round or triangle. You could call them something else, but that's pretty much all you can do. And statistically, you can't really do very much. You could say what is the most common value, for example. So you can do the mode. If you have an ordinal scale, then you have order. So you can't really permute things because then you get a different order. You can talk about median or percentiles, but it doesn't really make sense to apply the arithmetic mean, for example. My standard example here is house numbers. So we represent house numbers by integers, but that doesn't mean that we can add them up, for example, or average them. Interval scale are scales where we don't have a fixed zero. So the standard example is there, Celsius and Fahrenheit. So yes, there is a 0 Celsius, but it's not the same as the 0 Fahrenheit. 0 Kelvin is there, the 0 has an absolute meaning. So what that means is that we can talk about the ratio of temperatures in Kelvin. So we could, it would be meaningful to say that this body, this object is twice as hot in degrees Kelvin as this body. That would make sense. So you can take the ratios of kelvins with an absolute 0, but you can't take the ratio of temperatures of Celsius or Fahrenheit. But what you can do is take the ratio of differences. So for example, I could measure maybe my body temperature in the morning and in the evening, and I could do that on consecutive days. And then I could say the difference between my evening and morning body temperature today was twice as much as the difference between evening and morning temperature yesterday. And that would be, that quantity would be the same regardless of whether I would measure it in Celsius or Fahrenheit. So that's why these are called interval scales. So, so this is another table basically saying the same thing. What are allowable transformations? So for interval scales, we have affine transformations, and for ratio scales, we have linear transformations that are allowed. And also associated with each scale type are allowable statistics. So for example, only when you get to the interval scale does it become meaningful to talk about the arithmetic mean and the variance. Okay, so this is all well and good, but actually it's there's a lot more that you can say about scales. So for example, scales can be bounded from below with the fixed 0, but they could also be bounded from above. In fact, we are very used to that because counts in a confusion matrix or probabilities even are bounded from both sides. And that isn't actually, Stephen's system has nothing to say about that. It's also a bit rigid because, you know, we are pretty comfortable to even talk about Spearman's rank correlation statistic. Even if you have ordinal data, you map them to integers and that gives you some kind of idea of correlation, but under Stephen's rule, that wouldn't be allowable. So one would like to think that there is more that one could say about this, and there are some proposals. Of course, John Tukey has had some additional typologies. The most recent one that I could find was from a geographer, Chrisman, who has these kind of other categories, but there isn't a definitive account. So this, let me leave that there. It's kind of saying that, you know, we probably need to look a bit more at this. So what about the physics perspective? So the idea that physical quantities have an associated dimension goes back to Joseph Fourier. I think I may even have, oh, there we go. Go straight to Google Books. And he talks about, this is obviously an English translation, so he talks about dimensions here. So you see that in the second paragraph, every undetermined magnitude or constant has one dimension proper to itself. Okay, so so the idea is that quantities that have the same dimension can be added or subtracted. Of course, they need to use the same unit and use the same scale as well, but only quantities that have the same dimension can be added or subtracted. If you're dividing or multiplying quantities, then you're creating derived dimensions. So, for example, if your velocity is a derived dimension, which is length divided by time. Acceleration is another derived dimension, which is length divided by time squared. So you can multiply or divide quantities, and that gives new dimensions. You can add or subtract quantities, but then they must have the same dimension, and the difference or the sum has the same dimension as well. Of course, this is a choice. This is because we prefer addition and subtraction. So we gave addition and subtraction a special status in physics, because we could have taken, we could instead of length, we could have used sort of different scales like a logarithm of length or e to the power of length or things like that. And then we give different operation center stage, but that's what we decided to do. This is good as far as it goes, but it has issues as well. Actually, many quantities of interest are dimensionless. So, for example, angle is a ratio of lengths, and therefore angle is dimensionless, but at the same time, it does have units, which kind of seems a bit odd. Units can even cancel. So alcohol by volume has milliliters ethanol per 100 milliliters of liquid. So that's just a percentage. It doesn't even have a unit anymore. But more importantly is that in this system of dimensions, transcendental functions or functions that go beyond polynomials, you can't meaningfully apply those two dimensions quantity. So it's not meaningful to say that the dimension of the logarithm of a volume is somehow log volume. If you want to waste some time, then I would strongly encourage you to Google this, and you will see very heated debates among physicists of whether you can do that or whether you cannot do that. But basically, you will run into trouble whatever you do, because it's a bit unsatisfactory to first make the volume dimensionless by dividing it by the unit volume, and then you have a proportion, and then take the logarithm. But of course, logarithms is what we do in machine learning all the time. And my intuition is that if P is a probability, minus the logarithm of P is something like a number of bits. And for me, that makes perfect sense to think of number of bits as a dimension, which has a certain relation to the dimension of probabilities. But of course, it doesn't work exactly in the way that physics works. So we need something more flexible, particularly because clearly not every dimensionless quantity can be sort of added or subtracted to each other. So we need something a bit more flexible. So I don't have the answer to this, but I just want to point people a little bit to the computer science perspective. Because in computer science, we're used to thinking about types. And types are maybe a bit like what we looked at before. They have a structure, and they have operations on them, and they provide relative metadata about what you can do with them. And so But the important difference is that in machine learning or in data science or AI, the same quantity can have different types. And I'm going to illustrate that with an example with actually entropy. So entropy, so sometimes called Shannon entropy, is basically one way of understanding Shannon entropy is as an expected number of bits. Okay, so in information theory, if we have a number of possible messages and we have each message has a possible has a probability, then we can talk about what is the expected message length under the ideal encoding. We can try to get as close as possible to the most efficient encoding, and then we have an average message length. So in that setting, I won't go through the details, but the idea is that this is in a Haskell language, functional, higher order functional language. So probability to bits simply takes a probability and calculates the associated number of bits that the ideal encoding would use to encode that message. It's minus logarithm to the base 2 of the probability. Then we have an expectation operator, which does exactly what you expect it to do. So we have a distribution, which is a list of probabilities. We have a list of outcomes, and then we calculate an average outcome. Okay. And by the way, there are some philosophical issues there as well, because, for example, if you want to calculate the expected number of dots on a six-sided die, then of course the expected number of dots is 3.5, and there is no side of the die that actually has 3.5 dots. So there are some philosophical questions there as well, but let's assume that we actually can do this calculation. Then we have an expectation, and then we can combine these two and just say Shannon entropy is just the expected number of bits, where we use in the expectation the same probability distribution that we also use to map probability to bits. So this is one way in which Shannon entropy can be understood, but there are other ways in which Shannon entropy can be understood. And here is my example. Again, the details don't matter very much, but this is my encoding in Haskell of a different understanding of Shannon entropy through scoring rules. So the idea of scoring rules is that, let's say we have a log loss scoring rule, which is very popular in deep learning, but we could also have a quadratic scoring rule. And then we can, if we take that scoring rule as a parameter, so that the first argument of the function phi is a scoring rule, and then we also give it the probability and we give it a true class. So y is either 0 or 1. If y is 1, then we calculate the loss relative to 1. And if y is 0, then we calculate the loss relative to 0. We can do the same thing where the third argument is not a class, but another distribution. So we essentially do the same thing here. And then we can calculate what is known as a generalized divergence, where basically we calculate what the function S gives us for P and Q, and we offset that against this term. And this term is a generalized entropy term. Now, the point is, the details are not important, but the point that I'm making here is that this generalized entropy, if you plug in the log loss scoring rule, the generalized entropy again is Shannon entropy. But if you plug in the quadratic scoring rule, then this generalized entropy becomes Bernoulli variance. So essentially P times 1 minus P. So the point I'm making is that Shannon entropy can be understood via two ways, or more ways, I'm sure. And these two ways have different types. right? In physics, this wouldn't be allowed. You couldn't say, oh, if you interpret temperature in this way, it has the dimension such and such, and if you understand temperature in this way, it has a different dimension. Physicists would be very unhappy with that. But actually, in machine learning, we shouldn't be afraid of that situation. We know from decision tree learning that there are different ways of calculating the impurity of a leaf. And again, that goes back to these different choices of scoring rules. So my contention is that maybe types in computer science give us an opportunity to understand this more. Right. Okay. So I'm kind of through most of my talk. I'm just going to measure two more things. One is what about this story about latent variables? And I will very briefly also mention causality, and then I'm going to conclude. So I already made the point on this slide. So there is this thing called item response theory, and the basic idea is the following. So again, the details are not so very important, but we have essentially so the population, the plate N here, that indicates a population of questions or items. The plate M here indicates a population of students. Now, each student has an ability, which is indicated here by theta, and each item has a difficulty. Just ignore this variable A here. Let's just look at difficulty and ability. Now, the idea of item response theory is that the probability that a student answers a question correctly is proportional to the difference between the student's ability and the question's difficulty. So if the student is more able than the question is difficult, they have a more than 50% chance of answering the question correctly. So there is some kind of logistic curve there. So, and that's what you see in this factor graph. So we take the difference of the ability and the difficulty, that gives us the difference here. We plug that into a logistic function, and that gives me, and we sample from the logistic to decide whether the student gets the question correct or not. And the point is that only that last bit is observable. So we know whether the student answers the question correctly or not. And from that, we need to estimate what these latent quantities are. We, of course, don't do that with one question and one student. We do it with the whole set of students and a whole set of questions. The parameter A here is called discrimination, which is basically how well does a question separate between good and bad students, essentially. So we took this and we modified it a little bit because we liked it more where actually the difficulty and the ability is measured on a 0-1 scale. So we used beta distributions rather than the logistic curve, but that's not that important. Then we get these kind of item characteristic curves. So these curves tell me about a particular question, how how likely it is that the student of a certain ability is likely to answer the question correctly. Right. So, and yeah, this last comment is important. So there's a big debate in the cognitive science literature about discrimination, because discrimination can be negative, which means that more able students are more likely to get the question wrong. You could think of that as trick question. So a trick question is something where maybe a student who is not very good doesn't even see that it's a trick question and just goes for the intuitively correct answer, whereas more able students can overthink it. So we applied that idea in trying to detect noisy examples. So the hypothesis here was that better machine learning models would be more likely in getting tricked on noisy examples and trying to overfit those. And in this AI stats paper, we showed that we got some success with that. So the idea is really to look at the ability of machine learning models, but also to look at the difficulty of data points. And some data points are easier than others, and we use that to detect which might be noisy data points. And another example that another application that we did in this context is where now we don't take data points as items or questions, we take whole data sets as items. And the idea here is, can we do adaptive testing in machine learning? So the idea of adaptive testing is that you kind of do a binary search in ability space. So you give a student an averagely hard question. If the student gets the question right, you give them a harder question. If the student gets the question wrong, you give them an easier question. And so after a few questions, you have an idea where in ability space this student should sit. And the idea is, can we do something similar in machine learning? So rather than giving a machine learning model 100 data sets, maybe we just want to give it 5 well-chosen, well-calibrated data sets of which we know the difficulty. And this paper here showed that we had some success with that. So the idea is that at the end we get whatever the value that we would have got if we gave all the test sets to the algorithm. And we show here that we can converge very quickly to a value that is pretty close to what it would be. So even with less than 10 data sets, you can save yourself the trouble of applying the model to all the more than 150 data sets. Okay, so I'll start to wrap up now and then open the floor for questions. So I think ultimately, this is not the whole story, because empirical machine learning needs to make causal statements. It's not enough to know that algorithm A outperformed algorithm B. We want to know why. For example, because the classes were highly imbalanced. Or we can then turn this into a counterfactual. We could say, if we rebalance the classes, that's an intervention which we can apply, the difference in performance would disappear. Now, some people do ablation studies in machine learning, and that goes in this direction. But I think this is really, we want causal statements. We want to understand why one algorithm outperforms the other, not just observe that an algorithm outperforms another. And actually, this kind of causal inference using interventions is possible in empirical machine learning, unlike, let's say, in medicine, where once we give a patient the drug, we can't sort of, take the drug back and start all over again. Whereas in machine learning, we can, because the algorithm does not have memory of what data sets it has seen as such. So we can just reinitialize the whole thing and do it again. So causal inference of this type should not be hard in machine learning. So just to conclude, the message here is that whenever you do measurement, and performance evaluation is an act of measurement, you need a measurement model that has several components. You basically need to understand your observable performance indicators, and you need to understand what are allowable statistical operations on them. You need to realize that what you can observe is not necessarily what you're interested in. So you need to have a latent variable model, and you need to do some kind of causal inference as well. So that's all I've got for you today. So as I said, there is project here at the Turing Institute with some more material, some more talks. There's a code repository here. There is more information about the papers here. And there is a large list of names of people who with whom I've collaborated on these topics. So let me stop there, and hopefully we now have the opportunity to have some discussion.
Yeah, thank you very much, Peter, for this very interesting and thought-provoking talk. So the floor is open for questions, comments, remarks, opinions, whatever you want. So far, I have nothing in the chat. You can also ask, I mean, at least those people in Zoom, you can also ask questions directly. So please raise your hand. Marcel, you are the first.
Yeah, thank you for the very nice talk. Very interesting and intriguing ideas here. What I thought about is, especially for your last example of these counterfactuals. So why did algorithm A outperform algorithm B? This is again based on the measurements, right? Which you kind of criticized in the very beginning. So this feels to me like a circle, devil's circle, just going up the spiral. Is this going into an infinite regress later on, or what is your thought about this?
Well, I don't think it will lead to an infinite regress, as long as we don't assume that, you know, we don't take the measurement for the real thing. So, for example, in learning theory, we kind of, you know, we try to estimate what you know, how much data I need to use in my testing to get close to, you know, to get close enough to the real value, which I don't know, right? So that's the that's one kind of argument. It's not a causal argument, but at least there is this idea that I have something that I know, and I have something that I want to estimate, and under certain conditions I can say something about how close I can get to them, or under certain conditions I can say something about that I will always be far from it, right? So that's not the causality side of things, of course. The causality always requires an intervention and comparing two kind of different measurement scenarios and see what that tells you. So I don't think it necessarily leads to an infinite regress, but it requires it requires careful thought about what we are doing here. And I would think every act of measurement or every act of estimation or every act of prediction requires a model in itself, a measurement model. So it's not enough that the machine learning paper says, this is our experimental protocol. The protocol itself needs to be justified. What's your hypothesis? Why are you measuring? And then the interpretation step needs to come. What do my measurements tell me about the hypothesis that I started from, right? So I think that I get a bit frustrated with this kind of current state of affairs where the culmination of the paper seems to be the big table at the back with the bold numbers in the right columns. And I think this is a starting point. This needs testing, right? So we're in science, we need to try to see, is this always the case? Can we falsify this? Can we break this? Are there situations where this doesn't hold? And it's that kind of inference that is needed, and people often stop short from there.
Okay, Marcel, that answers your question, I guess.
Yeah, thank you very much.
Okay, thank you very much, Peter. And then there is Karim, please.
Hi,
Karim,
thank you for this very interesting talk. I have a question. I have two questions. The first question is about one of the first slides. It was named the physics perspective, and mainly it was about the units of the measurement that we do and the fact that we cannot sum measurement of different units.
Okay,
yeah,
let me
mainly
just find this. So here.
yeah, exactly. It was this slide. Yeah, so mainly now the issue is that when we consider real problems, there's for sure multiple dimensions to evaluate them, and somehow as data scientists or we need to take a decision. So we have probably, for example, different machine learning models that are getting different evaluation scores through different dimensions, and somehow we need to merge all these numbers. So if we cannot sum them, how could we proceed?
Okay. Right. So let me first say, if we just are happy with the physics perspective, then we would say accuracy, F measure, all these things are somehow dimensionless quantities. They're all on a 0-1 scale. So a physicist would very happily add them up, right? And say accuracy plus F measure, or even average of accuracy of F measure, or even harmonic mean, or whatever it is that you do. So for me, that is unsatisfactory. So whenever you add things up or you take the arithmetic mean, you're saying something about the scale of those quantities, right? So let's take probabilities as an example. Because probabilities are interesting because there are different kinds of allowable operations. So it is perfectly valid to add probabilities. But what it usually means is that you have two mutually exclusive events, and you're basically calculating the probability of one of them happening, right? If they're not mutually exclusive and you add them, then you need to do Poincaré's law of inclusion exclusion, because then you need to subtract their overlap, right? So you can add and subtract probabilities, but it says something about what it is that you're doing. You can also multiply probabilities, and then it says something else about what you're doing. So if I multiply P1 and P2, maybe what I'm doing is calculating the joint probability of two independent events, right? And if they're not independent, then again, by multiplying them, I've kind of, I've either overestimated them or underestimated them, and I need to apply some kind of correction and so on. But notice that there is no confusion about when it is valid to add and when it is valid to multiply, right? So, and let me give you one other answer to your point. What is nice about the physics perspective is that there is something called the I can't remember the name now, but there is a theorem that under certain circumstances, just knowing the quantities allows you to derive the actual relationship between the physical quantities. Sorry, let me say that again. By just knowing the dimensions, it is possible to sometimes to derive the physical laws that relates those dimensions. Right. So if you say I have length and I have time and I have speed, and if you know that speed is length divided by time, that allows you to derive or at least debug some of the expressions, right? So, and that's, I think that should be possible in machine learning. If a student comes to you and says, I derived this formula, which is P1 plus the logarithm of P2 squared. And you're kind of thinking, wait, what's happening here? This doesn't make any sense. That's some kind of dimensional analysis that's going on in your head. Whereas if somebody says, It took me a long time to understand the formula for entropy, for example, because minus p log p is not that obvious, right? Because if I bring the minus p inside the logarithm, then I'm basically talking about the logarithm of p to the power p. What on earth is p to the power p? That is not at all obvious. So if you then unpack that and say, well, there are these two things, the log of p gives me bits, and then I use the same distribution to calculate an expectation. Okay, that makes sense to me, right? But I think the way forward here is to come up with a theory that similarly allows us to distinguish between expressions that make some sense and expressions that are clearly nonsense. I'm not sure if I'm answering your question in detail, so please ask a follow-on question.
Yes, you did answer my question. Just summarize, I think. What you told me is that if I have multiple dimensions, multiple measurements, I should not just sum them to summarize them in just one number, but maybe I should think more about the units and think maybe about multiplying them or things like that. So it should not be automatically a sum. It could be something else. And in all cases, I need to justify my decision to the reader.
That's exactly
right. Thank you. And I have also a second question, which is about the last one of the last slides, the adaptive testing. In that slide, you say that somehow we want to have an adaptive test. Mainly, we try to use something like a binary search. So we try to ask an average difficult question to the student. If he answers correctly, then we move on with a more difficult question, let's say. We're trying to apply that to machine learning, but the thing is that you know that for binary search, we need to confirm that hypothesis that for sure the student will answer, for example, questions from difficulty 0 to 60, and he's gonna not answer correctly the rest of the questions that are harder. So it should somehow be continuous. I'm not sure if we also move to the machine learning example, we will be able to keep this hypothesis true.
Okay, so is your question about, I mean, it's true that if you only ask one question, then of course you can only pinpoint somebody in an interval. And that's true for 2 or 3 or 4 or 5 questions as well. But maybe often it is enough to pinpoint them in an approximate interval. Maybe you don't really need to know the exact number. Is that what you're asking about?
Yes, exactly. It's going to be somehow an approximation, not the exact evaluation. But yes, it looks like with the numbers that you gave later that it gives good result anyway.
Yes, but it's really about, okay, so keep in mind that the thing that if we look at all the data sets, the thing that we are measuring is still not necessarily the thing that we are interested in. So it is always a debate whether you want to measure precisely something that's only a proxy for something else. Maybe it's enough to imprecisely measure something because it is a proxy of something else. So that's kind of the philosophy here as well. Of course, it goes against the idea of, a statistician might say, well, you lose statistical power. You only use 5 data sets. But I think we are getting overly concerned about statistical power. Just to give you one example, UCI data sets became a kind of benchmark at some point. On the UCI data sets, there is a data set called mushrooms, where pretty much anything that you try gets you 99% accuracy. This is completely pointless. This is, if you add that to your data sets to get statistical power, that's clearly nonsense. That's the equivalent of giving students marks for asking the question, how much is 1 + 1? You kind of, it's pointless. We all know it's pointless, and still we do it. So I think it's more important to to have well-calibrated data sets where we know roughly how hard or how easy they are. Do they have linear? So how well do linear models perform? Do I need deep networks? Do I, so there's actually quite an old topic in machine learning called meta learning, which back in the day meant a little bit different from what it means today, but it's exactly that, trying to predict how well an algorithm will perform on a data set without actually running it. And so the idea was that you have meta features about the data set and you have meta features about your model, and somehow you have some theory about what you can say about the meta features of the model if you know the meta features of the data set. Right, so you can run simple models like decision stumps to get an idea how well a decision tree might perform if you increase the depth of the tree. So I think those ideas are still valid and interesting, and I think they will come back. Thank you for your questions.
Thank you.
Okay, thank you very much, Karim and Peter. Before giving the word to the next person, Maximilian, let me squeeze one question from the chat, from the YouTube chat in between. Although I'm not entirely sure what the question is, but let me read it. Peter, the following. So for real data sets, that some deep learning methods already hit the base error, but there is no way to be sure. For example, GNNs for CiteSeer, Cora, similar problem are now happening with ImageNet. So yeah, I'm not exactly sure now what the question is, but
so the base error rate is kind of sort of like an upper bound on what you can achieve, and maybe some models achieve that. Yeah, I'm not sure.
So I guess I don't know. Maybe the question is, how can you be sure whether you reach the base error or not if you have an empirical data set for which you can't compute it analytically or so? Or how can you be sure how close you are to the base error?
Yeah. Well, I'm not sure if I can answer the question directly, but there is, of course, with every act of measurement, there is a margin of error. There is uncertainty about even if you measure something that you think is observable, you make measurement error. There are various sources of measurement error. So that means that every measurement should have some kind of uncertainty region around it. And if you then make inferences with this measurement, you need to have some kind of way to carry the uncertainties and to propagate the uncertainties. So I guess that's what I can say in this context. I'm not sure if I have an answer to the question as posed, but clearly uncertainty does lead to an infinite regress, right? So you can have, if I toss a coin, I'm maximally uncertain about the outcome of the coin. I'm quite certain about the success, the probability of heads of the coin, but that I can, on each level of uncertainty, I can have a further level of uncertainty. And that never ends in some way. So that is a consideration.
Yeah, for base error rate, okay. I mean, one can certainly look also at learning curves, see whether or not they saturate, try to extrapolate them and such things. Yeah, but okay, good. So then, yes, Max, please go ahead.
Yeah, thank you so much for this nice talk. Especially this part with the SI units for machine learning was quite intriguing. Can you, I looked a little bit on the website now, can you elaborate a little bit further if there are current research works out there that you are investigating on in that regard? Because the first thing I heard was like, okay, nominal features, maybe what is a function that I can do with that? I might do one hot encoding or something, that this is a well-defined function in this nominal type of category of features or something. But from your talk now, I see that that's going a lot further than just that. And I would like to know if you already have some like theories or something that I might read up on or something like that.
Yes, thank you for the question. I mean, these are great questions, and I'm afraid I'm going to have to disappoint you in the sense that I don't have sort of any major breakthroughs that I haven't talked about today. So the idea of the SI system I was actually more talking, but not so much talking about features, but more talking about performance measurements. So the idea of the SI system is kind of twofold. So one is that we have decided that there are 7 fundamental dimensions, right? So we basically have length, time, temperature, and I can't remember, weight or mass, and then a bunch of other, right? So, and that's kind of, and we are satisfied that to describe our physical world and to measure our physical world, these are the 7 dimensions. And there is some choice there, of course, because we could also take, let's say, maybe velocity as fundamental and then take time as derived or something like that. But we made those choices. And then in addition, we make choices about what are the preferred units and the scales, but we allow other units and scales as well. So in machine learning, I would think about that in that SI system, there would maybe something like entropy, for example. But whether entropy, already from proper scoring rules, entropy and variance are kind of very closely related, right? And there is this notion of generalized entropy that can be sometimes instantiated to Shannon entropy and sometimes instantiated to Bernoulli variance. So I would be thinking, what are the fundamental quantities? I mean, entropy, probability bits. I'm not quite sure what shape that would take, actually. But coming back to your question about, so I have a logic background, and from a logic background, I think one-hot encoding are terrible things because you throw away, a logician would say you throw away so much information, right? You start by knowing that this is a nominal feature, so they're mutually exclusive. And you translate it into a bit vector whereby it so happens that exactly one bit is 1 and the rest is 0, but further down the line, you don't have that information anymore. You treat it as any other bit vector. So there's a clear loss of information there. Whether it's a bad idea, I don't know. It's certainly invertible. So, in that sense, it's maybe not so bad, but I hadn't made that connection. That's an interesting one. So think about the system where one-hot encoding is good or not. In my book, I played with things like, so some of you may be aware of the idea of classifier calibration. So getting calibrated probabilities out of classifiers. So, that if you predict 0.7 positive class, then if you collect 100 predictions of 0.7, then you would somehow hope that 70 of those were actual positives and 30 were actual negatives. You can actually do this on individual features, because individual features are can be classifiers, right? If it's a real valued feature, you can put the threshold and then you have a classifier, and you can ask whether this classifier is calibrated. So I think we can do a lot more in machine learning to transform features even before we put it in the model. Like, you know, if you know what the class is, so what would be the meaning of that feature? Well, I have some, I don't know, I have, let's say we have height of a person, and maybe a silly example, maybe our classes are male and female, and then we can say, okay, a height of 1.90 meters translates to a proportion of, you know, people with this height, maybe 72% of them are male. So now I've transformed this feature into a different scale. I haven't, and it's not really invertible in that sense, but maybe if I insist that it's a monotonic mapping, then maybe it is invertible. So we can certainly do much more creative things than just one hot encoding, because otherwise our neural network can't deal with it, right? That is just one reason of doing it, but there may be other reasons, other ways of transforming features in such a way, because you can do this with nominal features as well, right? So you can say hair color, let's say discrete feature, your class is male or female, and you can still translate hair color, red hair, ginger, you know, what percentage of people are male or female, and that is a numerical feature. So you can go from discrete to numerical, actually, from nominal to numerical in that sense. And I talk a little bit about that in my book. So I think there's much more creative stuff that we can do with features that we don't think about.
Thanks for that. I would actually also argue that because it's such a creative task is why we apply neural networks in the first case, because we just let them learn all of these creative transformations themselves and then be done with it. Like, but yeah, it's quite an interesting thought to have something like these SI units for machine learning. This quite resonated with me. Thanks for that.
Yeah, okay, thanks for your question.
Okay, so we are already a little bit over time, but maybe one quick last question with a quick answer. Otherwise, we can also take that offline, Peter. So in the beginning, you've been speaking about measuring performance on test data and things that might be troublesome. So for example, you average in cross-validation where you shouldn't average and these things. But what we are actually interested in machine learning most of the time is generalization performance, not test performance. So would you subsume this under this notion of latent feature that you also mentioned in connection with cognitive psychology? So for example, would the ability of the student, which you can't measure directly but only indirectly, would that correspond to the generalization performance, for instance, of a machine learning model or so?
Yeah, that's a great question. Ideally, that's what you would want, but the problem with latent variables is that, and maybe I'll stop sharing now. So the problem with latent variables is that you get to choose the unit and the scale yourself, right? And that's actually what was the difference between the first IRT model, which is using logistic curves. And basically that means that in that model, difficulty and ability are on a scale from -infinity to +infinity, right? Whereas when we went to our beta IRT model, we actually measure difficulty and ability on a 0-1 scale. So that already shows that you have the freedom to do that, and there is no experiment in nature that you can do to tell you which one of these two is right. Okay, so same story with you know, we're so used to thinking in terms of personality tests and so on. All this is made up stuff, right? So saying extrovert versus introvert and so on. This is not observable. This is somebody somewhere who has come up with a fancy model, 5 latent variables, and sort of, and okay, so they come up with a probabilistic model, they fitted the model, and now we have a post-Jungian personality test, blah, blah, blah. So it may be helpful, it may not be, but it's you can never, it's hard to validate these things, right? So so to come back to your question, so can you come up with a model whereby future test, performance on future test data is somehow the latent variable? I suppose maybe it would become some kind of sequential model, right? So you have this idea that you test today and you try to predict what your performance is on the test set tomorrow, and then you actually test tomorrow, and then you kind of, maybe there is something that you can do in that sense. But yeah, it's a great question. I don't know whether this makes sense.
Okay, all right. Peter, I think we have to make a cut here because we are really running over time. So I would like to thank you once again, Peter. It was great to have you here. Very interesting talk, very nice discussion. Also thanks to the people attending and engaging in the discussion. With this, I would like to close our seminar today. I just remind the people participating in the fireside chat, please just stay in the room here. The same, of course, for Peter. Yeah, that's all from my side. I don't know, Marco, do you want to say something more, or should I just close the seminar at this point?
You can just close. That's
okay,
fine.
So with this, the seminar is closed, and hope to see you next time again. Have a nice evening. Bye-bye.